students, this is Dr.V Siva Nagaraju from IARE. Today we are going to discuss some problems on error control codes. Actually, error control codes have come in Aeronautical and Digital Communications course in the last module, which means the 5th module. So, in theory, we see different types of codes, error control codes, like black codes, cyclic codes, conventional codes, like that. But today we are going to solve some problems on block codes only. Okay? Coming to the course outcome, this block codes is covered by module 5, and module 5 is covered by course outcome 6. So what the 6th course outcome says? Build the block codes for error detection and error correction in noisy environment. So here we are going to build the block codes. How to generate the block code? By using the block code, how we are going to find the error detection, and again how many errors are going to correct. Why? Because these errors are generated in noise. So when noise is increased, so there is some errors. There is a chance to produce errors. Okay. So in this session, we are going to solve some block codes, some problems on block codes. Okay. So problems on linear block codes. So this is the block code. So in this problem, we can say the generator matrix for a 6,3 block code is given below. So this is the G. So actually this totally is the matrix, full matrix. Okay. So this is a 6,3 block code. So generator matrix for a 6,3. So we are going to generate a block code. What is the size? 6,3 by using generator matrix G. So what is the G size? G size is 3 by 6. Why? Because 3 rows we can see and 6 columns. So it is 3 by 6. So find all the code vectors of this code. So how many code vectors or how many vectors are there in this code? What is code? Block code. So here one thing, in the block code, the generator matrix or the parity check matrix or the generated code or the syndrome, whatever it may be, they are in the blocks, they are in the size of matrices. So simply you can say it is block. Okay. So now we are going to find the code, block code, by using Z. Okay. So coming to the solution. So first you go to write the given generator matrix. G is equal to 1 0 0 0 1 1 first row, second 0 1 0 1 0 1, and third row is 0 0 1 1 1 0. So this is the given G. One second, you can go to check. Okay. Yes. So here you can see, by observing this generator matrix, here I can say the first part. This is the first part. This is nothing but identity matrix. You can see 1 0 0 0 1 0 0 0 1. What is one? This is a 3 by 3 identity matrix. And the remaining second part of the generator matrix, this can be called as coefficient matrix. This is coefficient matrix P. Okay. So when you are going to generate a generator matrix by using coefficient matrix also. So in some problems, they may give coefficient matrix. You are going to generate generator matrix. How? Just we are placing the identity matrix beside this coefficient matrix, then we can generate the generator matrix. Okay, this is a given G. And what about given 6, 3? We are going to generate a 6, 3 block code. So here 6, 3 block code. So what resembles N, K? N is the code length, K is the message block. So in this problem, find all the code vectors they given. They don't say 3 code vectors or 5 code vectors or 8 or 16. Then how do you find? Here, simple one. Here they given K. What is the K? Message. So 2 power K gives 8. So totally we are having 8 code vectors in this block code. The message size is given as 3. So if you substitute 2 power K, 2 power 3 is 8. So 8 code vectors are there in our block code. So 8 vectors we are going to find by using this K. Okay. So here G is in the form of I, K, P. You can write this one in this form also. IK augment of P. IK. What is IK? Identity matrix with a size of 3 by 3. With a size of 3 by 3. So why K size is 3? So it is 3 by 3 size. So the identity matrix is 3 by 3. Why? Because this is given as 6, 3. K is the message size and P is the coefficient. Okay. So here G equal to IK augment of P. So here we are going to write this IK is 1, 0, 0, 0, 1, 0, 0, 0, 1. And P, the coefficient matrix 0, 1, 1, 1, 0, 1, 1, 1, 0. This is my coefficient matrix. In some problems, they may give only this coefficient matrix. By using this coefficient matrix, we go to generate G. From the G, we are going to generate the block code C. Okay. So let us obtain the parity. Here we are going to obtain the parity bits. So why? Because if you generate any code, the code must contain the message bits and parity bits. Why to generate these parity bits? These parity bits are helpful for error detection and error correction also. So that's why we must generate the parity bits. Okay. So how did obtain the parity bits? So here taking the coefficient matrix, from that coefficient matrix we are going to generate G and again go to parity. So 3 parity bits. Why? Because my size is 6. What is the size? My code size is 6, 6, 3. So the code size is 6. So here 3 parity bits are going to generate in addition to the 3 message bits. Okay. So C0 is equal to M0 into 0 XOR M1 into 1 XOR M2 into 1. So we have a doubt where you get this M0, M1 and M2. So for that, here C0, C1, C2, these are the three parity, that is equal to M0, M1, M2 into this coefficient 0, 1, 1, 1, 0, 1, double 1, 0. This is my coefficient matrix. So by using this coefficient matrix, I am going to find this parity. Okay. So M0, M1, M2. So M0, the first row, is multiplied with the first column. So M0 into 0, XOR operation of M1 into 1, M2 into 1. So in between they are having XOR operations. Like that, C1 is equal to, again to the, this is the first one. And now this is the second column. So M0 into 1 XOR M1 into 0 XOR M2 into 1. So this is my second pattern. Like that. Third one, C2. So this is the my third column. So M0 into 1 XOR M1 into 1 XOR M2 into 0. This one, these three. Okay. So when you go to substitute the M0, M1, M2, then you are getting the possibility parity bits. Okay. So for example, my M0, M1, M2 all are zeros. For example. Okay. Why? Because already we know that 2 power k, that is 2 power 3. So the message size is 3. So you get 8. So 3 size means 0, 0, 0. And next 0, 0, 1. Okay. So the first one is 000. So now we are going to multiply this M0 into 0. So my M0 is 0. So 0 into 0, 0. XOR M1 also 0. So 0 into 1, 0. XOR M2 is also 0. So 0 into 1, 0. So first row C0 is, C0 value is 0 XOR 0 XOR 0. So simply it is 0. Next C1. So for C1 again M0 is 0. So 0 into 1, 0 XOR M1 is 0. So 0 into 0, 0 XOR M2 is 0. So 0 into 1, 0. So this one also 0. Likely C2. M0 is 0. So 0 into 1, 0. XOR M1 is 0. So 0 into 1 is 0. XOR M2 into 0. My M2 also 0. So 0 into 0 is 0. So the first message bit, the parity bits also zeros. Okay. So you can see 0, 0, 0, 0. The first three is message and next three is the parity bits. Okay. So like that we are going for the second one, that is 0, 0, 1. That means my M0 is 0, M1 is 0, but M2 is 1. Okay. M0 is 0, M1 is 0, M2 is 1. So first one is the message. So 0, 0, 1. This is my message. So what the parity is going to find. So again you go to substitute. M0, 0, 0 into 0, 0 again. The second one. So C0 is equal to 0 XOR M1, 0 XOR M2 is 1. So 1 into 1, 1. Now what is value? 0 XOR 0, 0. 0 XOR 1, 1. Next, C1. The C1 is this one, this formula. M0 into 1. What is M0? 0 here. So 0 into 1, 0. So first term is 0. XOR of M1 is 0. So 0 into 0, 0. XOR M2. M2 is 1. So 1 into 1. What do you get? 1. So here the final value also 1. Next C2. So what by C2? M0 into 1. What is M0 value? 0 here. So 0 into 1, 0. XOR M1 is 0. So 0 into 1, 0. XOR M2 is 1. But 1 into 0, 0. So final 0. So what is my C0? C0 is 1. C1 is 1. C2 is 0. This one. So this is the first code and this is the second code. So what they ask? They go to find all the code vectors. Okay. So this is the way how to find the block code. Okay. So here I am writing serial number, message vectors, parity bits, and code vector or simply code. So this is my code. So first message vector is, so once again here you go to write M0, it is going to clarity. So M0, M1, M2. So 3 parity, C0, C1, C2. Okay. So first 0, 0, 0. And second one 0, 0, 1. Third 0, 1, 0. 4, 0, 1, 1. Fifth one 1, 0, 0. Sixth one 1, 0, 1. Seventh one 1, 1, 0. Eighth or ones. So this is my message vector. For this message vector, we are going to find the parity bits. So already we see 2 examples. There is a first bit and second bit. So here 1, 1, 0. And here you go to write this M0, M1, M2, C0, C1, C2 side by side. This is my code. So 0, 0, 0, 0. So this one and this one, this one. So this is the code. Okay. So for messages 0, 0, 1, 1, 1, 0. Okay. Similarly, for 0, 1, 0, we got 1, 0, 1, 0, 1, 0, it is 1, 0, 1. Similarly, you go to multiply like this. So M0 value, M1 value, M2 value is changing. Okay, so this is the parity bits. C0 is a parity. To find parity, this also parity, these two. So totally 3 parity bits. Okay, so fourth one is 0, 1, 1. So again here 0, 1, 1. So 0, 1, 1. Fifth one 0, 1, 1. So 1, 0, 0, 0, 1, 1. Sixth one 1, 0, 1. So this one also 1, 0, 1, 1, 0, 1. And seventh one is 1, 1, 0, 0. This one also same. So here also we got 3. So 1, 1, 0. Okay. So here I am using G. There is a IK augment of P form. So here we can observe where the IK identity matrix is located. So here my identity matrix is located on the left hand side. So this is my message. Here you can see, for example, this code. In this code, 100 is the message. 100 is the message. 011 is the parity. So by observing the generator matrix, we can decide which side is message bits. So my ID matrix is located on left hand side. So my message bits are located on left hand side of this code. So this is the code. Okay. So here my code size is 6 bits. Why? In the problem they given 6,3 block code. The generator matrix for a 6,3 block code. So your aim is to generate a block code on which size? 6. So having 6 code vectors in my code. Okay. So by generating this code, the code size is 6, and on which side the message bits are located also identify by using this GIK P form. The generator matrix is very helpful for generating the code, for generating a block code. So this is all codes are generated like this. You also go to find all. If I give k value 6, so now how many message vectors are k? Simply 2 power 4. So what is 2 power 4? 16. 16 code vectors are generated. So 16 code vectors. So where it starts and what the message block size is? 4 zeros. Why? 2 power k. What is k size? 4. So 4 message bits like this 0, 0, 1 go to all ones, 4 ones. So this is my message. Same formula. You go to multiply this message with that parity bits. Then you go to 5. Okay. So coming to the second problem. What's the second problem? The parity check matrix of a particular 7, 4 linear block code is given by H. So this also like this. Like this. H. Parity check matrix. Find the generator matrix. and show the way to find the code vector. And third one is, what is the minimum distance between the code vectors? How many errors can be detected and how many errors can be corrected? So in this problem, they given all concepts what is in the block code. So in any block code, generated matrix is there, parity check matrix is there, and what the minimum weight or minimum distance between the code. So that is nothing but weight. So it is how many non-zero vectors. Why? In a code we call as code vectors or code elements. A single digit you can call as. So how many non-zero elements are there? That can be called as weight. That is the minimum weight. Okay. So by using the parity check matrix, we are going to generate the Z. Okay. So coming to the problem. So first let us obtain the P transpose matrix. So we know the P. P is the coefficient matrix and its transpose is PT. P transpose. Okay. Why? Because G is IK P form, IK augment of P form, where H is P transpose IN minus K form. This one. Okay. So in the given H matrix, this P transpose is there, and at the same time IN minus K identity. Why? Here what are the size given? 7, 4. My N, K is equal to 7, 4. So it means my N size is 7, my K size is 4. What is K? Message block. So it starts from 4 bits. Like already shown in the previous, this 4 zeros to 4 ones. Totally 16 message bits are there. So this is 16 message bits. We are going to generate 16 code words. Okay. But they are not given directly G. They given H. From that H parity check matrix, we are going to generate G. Okay. So here once again we see the H matrix. So H matrix is 3 ones 0 1 0 0, again 1 1 0 1 0 1 0 and 1 0 1 1 0 0 1. Okay. So here I am going to write my parity check matrix through transpose. So 1 1 0 1 0 0 1 1 0 1 0 1 0 1 0 1 1 0 1. What is one? 3, 7. 3 rows, 7 columns. Okay. So here you can observe it is in the form of P transpose IN minus K. Here we written H equal to P transpose augment of IN minus K. So in the right hand side you can see 1 0 0 0 1 0 0 0 1. What is one? Identity matrix. So what is the identity matrix size? N minus K. So what is N? 7. So 7 minus 4 gives 3. So my identity matrix size is 3 by 3. And this is my P transpose. So now can we generate G from H? Yes. Why? Because in H there is a P transpose form. Then you go to reverse, you get this G. Okay. So first you go to write the P transpose. That is P transpose is nothing but 1 1 1 0 double 1 0 1 1 0 double 1. This is my P transpose. From that P transpose, I am going to find the coefficient matrix of P. Okay. So just we go to transpose. That means rows to column, column to rows. So for example, this is my first row. So this first row converted into first column, and second row is converted as second column. Third row is converted into third column. Now the size is, here we can see 3 by 4. When you transpose this P transpose, it converts into 4 by 3 simply. So see how we generate 1 1 1 0. This is my first row. First row as converted into first column, and this is second row 1 1 0 1. So second row is converted into second column, and this is my third row. So third row converted into third column. So now what is the size? 1 2 3 4. 4 rows into 3 column. Okay, so the P size is 4 by 3. 4 by 3. Okay. So now we are going to adding this coefficient matrix to the identity matrix, or identity matrix add to the coefficient matrix. What it will. So let us add the identity matrix to the coefficient matrix P. Then you get the G. Why? Because the first bit is generator matrix. They ask what is the generator matrix. So G is IK augment of P. So I'm going to add IK. Now what is the K? Message bits. What they given? N comma K. 7 comma 4. So what is my identity size now? 4 by 4. Okay. So 1 0 0 0 0 1 double 0 double 0 1 0 triple 0 1. This is my identity matrix. This is my identity. So this identity augmented with coefficient matrix. Already you get the coefficient matrix 4 by 3 size. So there is 3 ones, double 1 0, 1 0 1, 0 double 1. So this is 4 by 7. See, 1 row, second row, third row, fourth row. So 4 rows. Columns 1, 2, 3, 4, 5, 6, 7. So 4 by 7. G sizes. That is reverse K by N size. Okay. So here we go to generate the all code vectors. So what is the formula? So first you go to obtain the parity bits. So the parity bits is C equal to M into P. M is the message block. P is the coefficient matrix. Okay. So what is the coefficient matrix size? Here 4 by 3. What my message? 4. Okay. So here you are getting 4 message bits, 3 parity bits. Okay. So here also C0, C1, C2. Okay. So here C0, C1, C2 is equal to message M0, M1, M2, M3 is multiplied with the coefficient matrix with P. So P size is 4 by 3. So this one is 1 by 3. So this is 1 by 4 and this is 4 by 3. So what the size of the parity matrix? It is 1 by 3 size. So this is 4 going to cancel. You get the first one 1 into 3. So 1 by 3 size of coefficient matrix are produced. When you go to multiply matrix of size 1 by 4 into 4 by 3, you get 1 by 3 size of matrix will produce. Okay. Okay. Coming to the C0, C1, C2 is equal to, so my size is 1 by 3. Here my matrix size is 1 by 3 and M0, M1, M2, M3 multiplied with P, 111, 110, 101, 0, 11. So what is size? 4 by 3. So this is 1 by 4. So get 1 by 3. So here I am going to multiply this first row with the first column. And again this row with the second column. Again this row with the third column. Okay. So solving, we obtain C0 is equal to M0 into 1. M0 into 1 XOR M1 into 1 XOR M2 into 1 XOR M3 into 0. M3 into 0. C1 is equal to M0 into 1 XOR M1 into 1 XOR M2 into 0 XOR M3 into 1. That's C2. Again M0 into 1 XOR M2 into 0 XOR, so this one is M1. Next M2 into 1 XOR M3 into 1, this one. So in between all are XOR operations. Okay. So M0 into 1 XOR of M1 into 1 XOR M2 into 1 XOR M3 into 0. Okay. So here you can simply say, so if M3 may be 1 or maybe 0. If anyone is multiplied with 0, what do you get? Simply 0. So again, simplifying these equations, simplifying above equations, we get C0 is equal to M0 XOR M1 XOR M2. The last one M3 into 0 is 0. Simply leave. C1 M0 into 1. So M0 XOR M1 XOR, here M2 into 0. 0. So M3 is left. Next C2 M0 into 1. M0 XOR M1 into 0. 0. So M2 XOR of M3. So by using this, you can generate the parity. Why? My message bits are changing from 4 zeros to 4 ones. So M0, M1, M2, M3. Okay. So in this way you are getting all the 16 message vectors of 16 code vectors. Simply the first problem, how did you find the all code vectors? So here also you get the all code vectors. But here 16 code vectors are generated. Because for example, we can see the last one, 4 ones. Okay. So here M0, M1, M2, M3. So for what is the C0? For the last one, this one I am considering. M0 is 1 XOR with M1 XOR with M2. Okay. So 1 XOR with 1. What do you get? 1 XOR 1, you get 0. So 0 into 1. 0 XOR 1, you get 1. Okay. Again, M0, 1 XOR M1, again 1. XOR with M3, M3 also 1. So here also same, 1 into 1, 1 XOR 1, 0. So 0 XOR 1, 1. Like this, 1. So 1. So for the code vectors, you are getting this one. What the size? 1 by 7. All code vectors. So in this way, we are going to generate all the code vectors. Okay. So let's take another message vector. So M0, M1, M2, another one we're taking. That is 0, 1, 0, 1. So in the last two taken 4 ones. Now we take a M0, M1, M2, M3. Okay. So C0 equal to 0 XOR 1 XOR 0. So here 0, 1 XOR 1. 1 XOR 0, again 1. So C1, 0 XOR 1, again XOR 1. So 0, 1, 1. 1 into 1, 0. So 1 XOR 1. Again C2, M0, 0 XOR 1. So what you got? 0 XOR 0, 0. 0 XOR 1, you got 1. Okay. So parity bits are 1, 0, 1. So now the code vector is first the message one. 0, 1, 0, 1. For this 1, 0, 1. So this is message and this is parity. Previously getting all ones, 7 ones. So 3 ones are these values. Okay. Now another bit is what is the minimum distance? D minimum. Minimum distance is nothing but minimum weight. So for example, when you're finding all 16 code words, how many non-zero elements are there? For example, in this code, 0, 1, 0, 1, 1, 0, 1. So how many non-zero elements are there? 4. For this code, D minimum is 4. Whereas the previous one, so in this one, this is 7. Why? Here all are non-zero elements. All are ones. So this weight is, here this weight is 7. So this is the weight of this code. So here this is the weight. So what is the weight? Here 4. Like that. So minimum weight. So minimum weight is the minimum distance. So after solving all this, you get this weight. Some codes having maybe 3. For example, 3, 4, 7 is there. So which is the minimum? 3 is the minimum. So minimum distance is D minimum is 3. Why? Because by using this D minimum, we can find the how many errors are there. Why? Because by using this error control codes, we can detect the errors, we can correct the errors. Okay. So here I am going detecting the error. I am going to detecting the error first. Then after I am going to correct. How many bits I can correct? That's also you go to find. Okay. So for example, here I am taking the minimum distance is 3. For example, I am considering minimum is 3. Now number of errors that can be detected is given by D minimum greater than equal to S plus 1. So this S is used to find the how many errors can be detected. Okay. So from this, my minimum is 3. So 3 greater than equal to S plus 1. So what is S? Therefore, S less than equal to 2. So that means we can detect 2 errors only. Here we can detect only 2 errors. Then how many errors can be corrected? That is D minimum greater than equal to 2t plus 1. Here t indicates how many errors can be corrected. Okay. So here you can write number of errors that can be corrected. That can be corrected is given by, that is D minimum greater than equal to 2t plus 1. So D minimum greater than equal to 2t plus 1. So 3 minus 1, 2. So what is my t? Less than equal to 1. That means only one error can be corrected by using this linear block codes. Okay. How many errors? I can correct only one error at a time. So I hope you understand well. Coming to the third problem. So here for a code vector x is equal to 0, 111, 0 and the parity check matrix H given below, prove that x H transpose is equal to 3 zeros. So here this also, this one. So what is maybe size? 3 by 7. So this is the given H parity check matrix. Okay. But what they ask? X H transpose is equal to 3 zeros. So we are going to prove this one. So first we are going to H transpose. The given H. We are going to transpose that H. What is H? Parity check matrix. So 1 1 double 1 0 1 0 1 0 double 1 1 double 0 0 1 0 and the last one is 0 double 1. This is my H transpose, parity check matrix transpose. So here 7 rows, so 7 by 3, 7 rows, 3 column. Okay, so what they ask? X H transpose. So in this they given X, they given H, but simply we are going to transpose. Very easy to solve these problems in block codes. Okay, so my X is equal to 0, 1, 1, 3 zeros, which is going to multiply of this matrix. 3 ones, double 1 0, 1 0 1, 0 double 1, 1 double 0, 0 1 0, 0 1 1. So this is 1 by 7. This is 7 by 3. So what you get? What's the answer? 1 by 3. So here this size is 1 by 3. So that means we are going to multiply this single row with first column, this row with second column, this row with the third column. So what do you get? Okay. So first 0 into 1, 0. Okay. So we can use a new page. So here there's 0 into 1, 0 XOR 1 into 1, 1 XOR 1 into 1, 1 XOR 1 into 0, 0 XOR 0 into 1, 0 XOR 0 into 0, 0 XOR again 0 into 0. This is the first row multiplied with the first column. Okay, come. Next, first row, the single row with the second column. So 0 into 1, 0 XOR 1 into 1, 1 XOR 1 into 0, 0 XOR 1 into 1, 1 XOR. So remaining all are zeros. Okay, 1, 2, 3, 4, 5, 6 XOR with 0. This is the second column answer. And third one, third column. You go to multiply a single row with the third column. So 0 into 1. What do you get? 0 into 1, 0. XOR 1 into 0, 0. XOR 1 into 1, 1. XOR 1 into 1, 1. XOR 0 into 0, 0. XOR 0 into 0, 0. XOR 0 into 1, 0 XOR this one. So we're getting 1 by 3 size. Only single row with 3 column element. Okay. So here you can see. So 0 XOR 1, 1. 1 into 1, 0. So 1 XOR 1, 0. So again 0 is 0 XOR with 0, 0. 0 XOR 0. So getting all are going to 0. This one first. And second column 0 into 1, 0 XOR 1. 1. 1 XOR 0, 1. Again 1 XOR 1, 0. So 0 XOR 0, 0. 0 XOR 0, 0. 0 XOR 0, 0. Coming to the third column. 0 XOR 0, 0. 0 XOR 1, 1. 1 XOR 1, 0. 0 XOR 0, 0. 0 XOR 0, 0. Again 0 XOR 0, 0. This one. So this is 1 by 3. So X into H transpose is equal to 0, 0. That's you prove or not. See, I can go to problem. Yes. X into H transpose is equal to 0. Okay. So these are the block codes. Very easy to solve these block codes, and error detection, error correction also easy by using block codes. Okay. I hope you understand well. Thank you. And the content of these problems are taken from Digital Communication by Sanjay Sharma. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.